All right, lesson 3, we're going to be balancing chemical equations today. Today's objective is that you will know the law of the conservation of mass and how it applies to balancing chemical reactions, and that you will be able to balance any chemical reaction with 100% accuracy. Now, what is the law of conservation of mass? It's likely that you learned this in middle school, but as a reminder, in a chemical reaction, atoms are neither created nor destroyed. The number of atoms will remain constant throughout the reaction. So, what does that mean? Well, a balanced chemical equation obeys the law of the conservation of mass. It always obeys the law. So, I'm going to highlight that obeys. To balance any equation, and the equations do not come balanced, when we write them, they will be unbalanced, and you must add the correct coefficients to balance the reactants and products. And we always want to do this in the lowest whole number ratio, which just means we want the smallest coefficient possible for each substance. In other words, the number of each element that we see on the left side of an equation must match the number of each element on the right side of the equation. So before we move into actually balancing equations, let's take a moment and make sure you know how to count atoms. So here's a simple example where we don't see any subscripts, no coefficients, and no parentheses. In this case, we know that it actually looks like this. There's an imaginary 1 behind each. So that means I would have 1 sodium, 1 oxygen, and 1 hydrogen. When there are subscripts, it's quite easy to do. We're just going to read whatever the number is, and that tells us how many of each element we have. So I have 2 C's and 4 H's. Now, when we add a coefficient, we must multiply the coefficient and the subscripts. So in this case, we're going to have 4 times 2 carbons, which is 8, and 4 times 4 hydrogens, which is 16. If you ever forget, you could always draw this out. We have 4 C2H4, so that's 1, 2, 3, and 4. And if you add those up, you'll find 8 and 16. And finally, what if we have all of these things? We have a coefficient, and we also have subscripts, but we also have parentheses. All right, so again, you could draw it out like this and count them, or we can just use a little bit of math. So I have Mg, O, and H. Let's go ahead and write that down. Magnesium, oxygen, and hydrogen. If we see something in parentheses, the number outside of the parentheses is distributed to both of the elements within the parentheses. So that means I have 2 oxygens and 2 hydrogens. I'm going to go ahead and write that down. And then here I see magnesium. There's no number after it, so we know we have 1. But we have to take into account this 4. So we're going to go back and multiply each of these values here by 4. So 4 times 1 is 4. 4 times 2 is 8. And it's going to be the same for hydrogen. So that's just a quick reminder of how you would actually count the atoms. In this first example, it's going to be KClO3 breaking down into KCl and O2. So we have 1 reactant, so this would be a decomposition reaction. Breaking down into KCl and O2. We need to balance this. So let's start by writing all of the elements that we see. I see KCl and O on the left side and KCl and O on the right side. So KClO. R stands for reactant side, P stands for product side. So I like to make a little table. Now, for the potassium, the K, I only have 1 on the reactant side, so 1. And on the product side, I also have 1. Cl, I have 1. Cl, I have 1. Oxygen, oh, I have a subscript of 3. So I have 3 oxygens, but over on the product side, I only have 2. So I'm going to have to balance this equation because my oxygens are not currently balanced. We must make them equal. Now, how do you make a 3 and a 2 equal the same number when you can only multiply? Well, we need the least common multiple. So 3 and 2, the easiest way to get those to equal would be by multiplying them together. 3 times 2 is 6. So we want to make this reactant side have 6 oxygens and the product side to also have 6. So 3 times 2 is 6. Now, I just did a times 2, so I have to be sure to write that in the front. That's the only place I'm allowed to put a number. And I even indicated that with these blanks. And over here, I wouldn't multiply by 2, I'd multiply by 3. So I indicate that by putting a 3 in the blank. Okay, so now I have 6 oxygens, and here I have 6 oxygens, but I have also affected the potassium and the chlorine. So now I have to distribute the 2 to both the potassium and the chlorine, so that means I actually have 2 over here. And the easiest way to fix that would be to multiply the 1 by 2. Yep, but remember I have to do it here. And that now gives me 2 potassiums, but I also have 2 chlorines, and we see that we have 2, 2, 2, 2, 6, 6. So you would balance this equation by putting a 2 in front of KClO3, a 2 in front of KCl, and a 3 in front of O2. And now for a slightly more complicated problem, we're going to look at one that contains a polyatomic ion. So for this example, let's still do the same thing. We want to indicate the number of each element, but there's going to be one thing we should do. If we notice that there's a polyatomic ion visible on both sides of the equation, so on the reactant side and again on the product side, we want to keep it together in our balancing table to make life easier. So let's do that. So I have H and H. All right, so I'm going to write H. Okay, I see SO4, which is sulfate, and I see it again on the product side. So I'm going to leave that together. Na, Na, and NO2, NO2. That's together as well. So I'm going to keep it together in my table. This will make it much easier to balance the equation as we start. Okay, so H, I have 2 as indicated by this subscript. And over here, I only have 1. SO4, well, there's no number out front yet. And this is just a single SO4. So 1 SO4. And over here, I also have a single SO4. Na, I just have 1. Over here, I have 2. NO2, let's see, I have 1 NO2. And over here, I also have only 1 NO2. So we need to balance H and Na, but in the process, we might end up having to rebalance some of the other ones. So let's just go ahead and start with hydrogen. I have a 2 and a 1. I need to multiply, so I should multiply this product side by 2 because 1 times 2 is 2. And when I do that, I have to indicate that with a coefficient. So now I have 2 hydrogens and 2 hydrogens. However, now that I've put this 2 in the front, this means that I also have 2 NO2s. So I need to write that down. And if you're not seeing that, again, just draw it out. I have 2 HNO2s, so that would be HNO2, HNO2. And you can see that I have 1, 2 NO2s, also 1, 2 hydrogens. Now let's do the NO2. Since we just unbalanced the NO2s, let's go ahead and fix that. Well, here I see that I only have 1 NO2 on this reactant side. So let's multiply by 2 to get 2. And remember, to indicate that, I have to put the 2 in the coefficient space. So now I have 2 NO2s. That's good. So 2 and 2. But I've also affected the number of sodiums. So now I have 2 sodiums as well. And you can see here that we now have everything equal. 2 and 2. 1 sulfate, 2 sodiums, 2 NO2s, and 2 NO2s. So this is how you balance an equation with a polyatomic ion. And finally, if you are still not understanding this and you need additional videos, you can always check out the 3 videos that I've provided here. You can also go back and watch this video as many times as you want and ask me any questions that you might have. Thank y'all for watching.